All right, I'll give it a shot. Sort of a big topic and has a lot of interesting sort of uh tangents you can go on. No pun. I don't do those. But so I guess I'll kind of kick it off and we'll see kind of see how far we get. Um, so let's see here. Share what? I'm gonna present our view.
Nice. I like the name. Just all of space.
Yeah. Okay, so let's go ahead and yeah, I didn't know what to call this thing. So spatial it is. I figured we could kick off by just talking about these sort of de facto conventions that are in Monty, and um, some explicit, some implicit. And I think we can all probably agree it'd be better to be explicit about all the conventions that happen to be in play. That involves Cartesian coordinate conventions, spherical coordinate conventions, rotations. I'm sure everybody is aware that we have a lot of different ways of representing rotations, and I don't really have a lot prepared for that. But obviously, the more we can do to try to um, eliminate inconsistencies and maybe one day abolish the scalar last quaternion from our code base. Not that I'm taking a side on scalar first versus scalar last, but if we're gonna pick one, let's just just try to stick with it. Um, and talk a little bit about transformations, which are stable so long as we agree on the conventions, and a little bit about reference frames and a couple examples involving the distant agent and targeting, finding the right actions to um, position the distant agent to look at something. And so let's just jump right into it. First off, there's um, a lot of different ways that you could decide which ones are X, Y, and Z of these three axes. So here I'm going to be using red for X and green for Y and blue for Z. Z for blue, blue for Z. So this is our convention here, um, where you got to imagine that this is an agent or a sensor that's facing the mug. So pointing to the right of us is the x-axis. The y-axis is pointing straight up, and the z-axis is pointing behind us. This was a bit confusing to me when I first came to the project because who has negative axis pointing forward? It just seems very strange. Um, it has the advantage though of leaving the plane that you're seeing like this looking kind of like normal, where you've got X going to the right and Y going up. And if you want to have a so-called right-handed coordinate system, um, which has benefits, and it's best to try to stay within them, if you're going to, then there's only one direction for Z to go. You can't have a right-hand coordinate system with having right X to the right, Y up, and then Z forward. That would be a left-hand coordinate system. Um, so
So hang on,
So,
in the
so,
right-handed coordinate system,
right.
which one is which?
So a right-handed coordinate system
Your
means,
thumb is X, your index is Y, and where you curl is where the Z should be. So if you put your thumb to the red, green to the index to the green, then
Yeah,
it tells you where the blue should be, which is forward, which makes sense.
and I guess that makes sense because it's kind of pointing towards, like if I held this at my head, then the Z is pointing back.
Yeah,
So that does
yeah.
seem to be
So
the same.
yeah.
Okay,
Depends
cool.
on how you
Thanks.
rotate your hand, I guess.
yeah. So
Also, I should say that we must follow the right hand rule, otherwise everything breaks. Like that's not a break rule that we can break, I don't think.
yeah, I'm not a physicist. It comes up in physics a lot. So, go talk to a physicist about electromagnetism or something, and they'll have things to say about the right-hand rule. All I remember is that, you can kind of like wrap your hand around and that's the direction of mag. Yeah, I didn't really understand it at a deeper level of what it's like or what its importance is in like in terms of actual physical reality, but in terms of our conventions, the there's kind of two nice things to know about right-handed coordinate systems. One is that if you're ever trying to remember which way positive rotation is about an axis, let's say I'm going to rotate around the x-axis here. Just imagine you're facing straight down it. So you're over here somewhere. I don't know if you can see my cursor. No, you can't see my cursor. But imagine you're sort of off to the left of the screen, staring straight down the positive
We can
end
see
of
your
the x.
cursor.
What's that?
We can see your
Oh, you
cursor.
can. Okay, so we're here, we're staring straight down. Then the remaining two axes are going to be spinning counterclockwise. So that's a feature of right-handed coordinate systems.
So counterclockwise is positive rotation and
Positive
clockwise
rotation.
is negative.
Yep.
Okay.
Yep. So no matter which, so if you want to know, like for example, you're trying to remember, oh, which way is yaw? If I say yaw 10 degrees, and I'm facing this cup, is that gonna spin me this way or is that gonna spin me that way? Part of me thinks it's gonna spin that way because I'm just thinking, oh, it's yaw and X is that way, right? Like X is positive over there. So I'm gonna positive spin, but no, it's not that way. If you stare down this y-axis, just mentally imagine it, then these guys go counterclockwise in this direction. So positive yaw is spinning that way.
The
Um,
way I do it is I just point my thumb in the direction of the axis and then I just curl my fingers. That's the way the others.
but everybody's got their
Yeah.
way. That was the way that's a lot of people use, and for some reason I just like play with my hands and never quite it just never really clicked for me. But thinking about staring down the axis, and then imagining the counterclockwise motion, that's kind of what clicked for me, or at least helps me kind of make sense of it. Um,
You can stare at your thumb down the axis, and then it's
yeah,
gonna go
I just stare at my
counterclockwise.
thumb now. All right, so the other thing to kind of be aware of is that rotations I mean, this is just kind of an interesting fact of three-dimensional space. They can be broken into two subgroups. There's left-handed rotations and right-handed ones, and you can't rotate a right-handed coordinate frame into being a left-handed one in the same way that you can't rotate your hands. I can't take a so if you're struggling to make two images look the same through rotation only, that means there's a good chance that either your controls are bad, which is common in programs for trying to get things to rotate properly, or there's a reflection of some sort, and meaning they're opposite-handed. So here's some other common conventions. We have X to the left here, Y forward, Z up. I think this is Matplotlib. It's also Blender. So if you ever try to go plot stuff in Matplotlib and it looks like this, or everything looks sort of spun by 90 degrees, it's because it's in this coordinate system. And you can imagine taking this x-axis here, and rotating this green guy towards the blue guy, and then we would have that. So you can transform between Matplotlib data and Monty data through one rotation about the x-axis by 90 degrees. Here's another one. This is in I guess this one's common in flight, which is kind of interesting. But point is, whether in like for example, Mujoko has a different coordinate 3D axes convention. So any data that comes and goes from Mujoko is going to have to do the corresponding transformation, or else things in Monty aren't going to work. We just have these assumptions built in, and they are due to Habitat, which uses the OpenGL very common 3D graphics convention, which is this one. So it's just some sort of something to keep in mind anytime you're interfacing Monty with any other kind of visualization tool or simulation tool. You just have to be, this is probably the first question you should ask yourself. Okay. Any further thoughts on that, or go ahead?
Yeah, the right-hand rule is mathematically important. Well, it's important because any rotation matrix, besides all the vectors having to be orthonormal, that the determinant has to be, if they're orthonormal, the determinant can be either +1 or -1, right?
Yeah.
Just linear algebra wise. The right-hand rule specifies that the rotation matrix has a determinant of 1. So
Right.
if you constructed a rotation matrix, like you have a quaternion, and then you put it to SciPy, like as matrix, it will create a rotation matrix with determinant of +1. So unless you want to give up that and define everything in left hand, which means not using any of those conversions, yeah, just saying the importance of like we must follow the right-hand rule.
But it's not impossible, right? Like Unity uses left-handed coordinate system, and it's a pretty successful simulation engine. So
Okay.
it's just the headache of conventions. But they're also the odd child out, as far as I understand, for the most part. But
Yeah,
this doesn't make it impossible. It just makes it you have to
very hard.
transform more.
Yeah,
And I was curious, yeah, Scott, let's say we are working with some new tool and it could be, yeah, new simulation, but it could also maybe be something like, yeah, I don't know, the VR setup that was tracking the coordinate of the tracker. Is there kind of a systematic way that we can kind of determine this if they haven't documented it well?
Yeah, well, I mean,
Because I feel like the closest thing is like, which I think is what we did in Crete, is like literally
Yeah,
take the tracker and move it through space
y-
and
yeah,
be like, okay, well that's doing this coordinate like axis, and this one is that's okay. So z is positive along that axis. That's basically what we ended up doing. But I don't know if there's something more elegant or kind of foolproof.
yeah. Oh no, that's like, let me see if I can just pull up the scale draw really quickly.
yeah. Remember Niels, you sitting in front of the screen and just like moving your hand in space.
I mean, that's exactly what
Using
you want
sensory
to.
motor
Yeah.
inference.
I mean, it's like exactly what all this stuff means is that if I can move um, one unit in some, who knows what that is, reference frame or coordinate system, and that ends up being, you know, 1, 0, 0 in Monty,
Right.
then you know that uh, X with respect to whatever weird coordinate frame you've got, that corresponds to uh, X hat. Let's call it X hat in Monty. And you just do this for each of the 3 dimensions, and you'll
Yeah.
exactly
I'm just
get,
gonna map it out.
if you've got some rotation matrix that goes from B to Monty, that's the basis vector of B with respect to Monty. That's the second basis vector of, system B with respect to Monty, and that's just the definition here. So this is exactly what you want to do. You just want to probe in each axis to uh, yeah.
Okay, cool.
so in Monty, our Euler angles are in XYZ. Is that the
Oh boy.
convention that we're following, or okay, I know. Okay, okay. I'll just wait. All right, let's continue.
So let's go to PowerPoint. Yeah, and sometimes you'll find stuff well documented for these things, but you can always kind of figure it out the way that Nils is suggesting. I do have a script that will convert between arbitrary, you tell it right up, down, right forward, and I wanted to kind of see if I could get into like a git gist or something before for this, but I didn't. But I'll put stuff, little utilities like that somewhere, so you can play with. And sometimes I'll use that. I'll say, uh, RFU to RUB, and it'll give me a transformation matrix, meaning right forward up to, right up back or something, and it just, spits it out for you. So this can be kind of handy when you want to rotate back and forth between different conventions. All right, here's another one that's kind of interesting. Spherical coordinates. They come up a lot when you're dealing with camera stuff, or when you have to issue commands, say yaw left by a certain number of degrees, or you're looking at some point in some sensor data and you're trying to find the associated spherical coordinates for that point. So there's a couple ways to define what these angles are going to be. There's two of them. There's an azimuthal angle, so rotation about the y-axis basically, so like this. And there's a elevation or a polar angle, which is like this. So probably the way most of us learned it is in the sort of mathy, physicsy way. Actually, math and physics don't exactly have the same convention, but for sake of discussion, I'll just say this one down here is probably the way we learned it, which is where we measure the azimuthal angle from the x-axis. So if you've got, this is a point in space, by the way. If I'm just looking at its azimuthal coordinate, you measure all the way from the x-axis like this, and to get its polar coordinate, you measure down from the vertical axis like this. It's more common in, say, robotics and things like that to do it the way we do it, which is that since we're staring straight down this negative axis, this negative z-axis like this, we measure the azimuthal coordinate away from the negative z-axis, spinning again in the sort of positive direction. And we measure the elevation up from the xz plane. So what that really means is that, so this is called the forward aligned zero angle axis convention. That means the azimuthal coordinate and the I'm not going to say polar coordinate because that, like, by context that usually means coming down from the vertical axis, unless somebody else has other experience, but that's just from what I can tell. Usually they call it elevation. But down here, 0, 0, in terms of the angles, they're aligned. So essentially we're the origin of these two angular coordinates is straight down the center here. So that their zeros are aligned. As opposed to the math and physics one where you've got a 0 down this way, that's your azimuthal 0 is that way, and your polar 0 is up that way. So let's see. Yeah, I think that's about all there is to that one. But
yeah, so I guess that means that in the math and physics one, that they're never really both 0. It's kind of like cosine and sine, where like as one grows, the other one shrinks or something, right? Like if you were facing in the direction of the red one, then the what do you call it? Polar one or whatever, the one from the top would be non-zero. Whereas in the one that we use in Habitat, they can both be 0 at the same time, and that corresponds to looking forward.
Yeah, I think that's right.
But wouldn't it be that if one of them is 0, the other one has no effect?
Has no effect.
Like if you have 0 for the red one, the line is just up, so it doesn't matter how you rotate along the green one.
That's a fair point, yeah.
Well, rotating around the green one,
I mean, I guess it depends on, you could still kind of rotate.
Coordinate, right?
But yeah, I'm talking about the math version now. I think in the robotics one, it's different.
0, 0 is undefined, right? Like it's not a point.
Say it again.
Yeah,
0, 0 is undefined. It has to be 0, 90.
Right.
You can't get to 0, 0.
Yeah, unless you're in the origin, I guess. So the
Yeah, because I think if you're a 3D object, you could still rotate about the green vector, even if your polar one is 0.
Yeah, you mean if like the little black dot is some kind of shape that
Yeah,
then could still rotate around its own axis?
yeah.
Yeah, if we're not
But
just
then
talking
that's
about a
maybe
point
mixing
in
up
space.
axes and points. Yeah. Anyways, it doesn't really matter. I guess I was just trying to check my understanding. But yeah, this is a helpful visualization.
So, sorry, Scott, I think I missed it. If I were to ever Google which convention is used where, what are the terms for these?
Forward angle zero, forward align zero angle axis. That's the
yeah,
mouthful.
forward line zero angle axis convention.
Okay.
So
Yeah.
here's my word of warning about Googling for the transformations between the two specifically is that well, you're just always going to have to do this game where you're like, okay, so they call that one the X, they call this one the Y, and so you're kind of always kind of doing these internal, substitutions for this axis and that axis. And it can get confusing pretty quick. And so when you see if part of your Googling involves the coordinate transformations between the two, that's where both conventions come into play. So the exact form of these transformations between the two depends on both conventions. So
We have like a combinatorial
yeah,
number of convention flavors.
yeah. So
Wow.
here they are. Moving on. No, just kidding. You read about them yourself.
I
So
just realized I just come up with how to like remember the forward align zero angle. Is that in like forward? So basically, what you consider forward, so we just said that in the first slide, Z is kind of pointing into you, right? Like your thumb, or not your thumb, but so forward means positive, like Z, and that's considered zero angle. So if something is looking at it without any rotation, zero angle, then
forward is
that's
negative Z. Is
forward. Yeah.
that what you
Forward.
said?
No, forward is positive Z.
Forward is negative
I guess
Z.
not in
Not
Habitat
in
or
Monty.
not in Monte.
We're looking straight down the negative. So this is our camera here. This is our little camera frustum. We're
Uh,
staring this direction.
yeah. Forward is negative Z. Yeah, but that angle, like that, basically the whatever direction you're looking at is your rotation.
Yes, exactly. I think the way I kind of think of it is exactly like that, which is like if I'm a camera staring down this axis, then dead center is 0, 0 for both angles. Which you
Yeah,
can just say like,
which
how
makes
much
a lot
do
of
I
sense
have to
from a
rotate?
robot
What's
perspective or
that?
whatever. Yeah.
Yeah, it makes
Yeah,
sense
Sorry,
for
yeah, it's just that it
robots.
makes a lot of sense from a robot perspective or
exactly.
whatever.
Yeah, yeah. It's like, how much do I have to
Yeah.
rotate left? None. How much do I have to rotate up? None. That's 0. Um, okay.
Question.
So,
Are you gonna skip this again? Cause I
no,
had.
go
Are you
ahead.
skipping it or?
No, no, I'm not
Okay.
skipping it. Okay, so uh the axis orders is pretty straightforward, as in, let's say you have a different, X, Y, Z. You just simply swap out the letters for the most part. And these, if you want to change them. Um, as long as you remember which one's the vertical axis, which one's the horizontal, and so on. The catch
So
about
as in, I'm sorry, so as in like Cartesian spherical, that first top left one could be rewritten as right-handed axis squared plus up vector squared plus
right.
backward vector.
Yeah. Yeah.
Okay, and then
Or
just
forward, backward, whatever you call I mean this is the nice one. I wouldn't worry
yeah,
about
that's the nice one.
uh,
That's maybe not a good example. I guess the second one it matters, but yeah, a
yeah.
lot.
So the second one, you'll probably see this one written differently if you look up how to do this conversion, because most texts don't have the negative z-axis as forward. Because we do have the negative z-axis going forward, we have to drop this negative sign in here, and that actually converts us temporarily to left-handed because
Question.
it makes the determinant -1 by multiplying a coordinate by
Question.
-1, which we then have to undo here.
Question.
Yeah.
You said drop the negative sign and then you pointed at negative z. What do you mean by drop?
Drop in. Sorry.
Okay, thank you.
You have to drop it from your stack of negative signs into this equation.
Thank you. Appreciate it.
Yep. So yeah, so that's one thing to be aware of for this guy here. Trying to get the azimuthal coordinate. That's a mouthful, azimuthal. I'm trying to reserve yaw for like an action, like a displacement more than an actual sort of
Kind of like
fixed.
rotation versus orientation.
Yeah.
Sometimes talked about.
Yeah.
Thanks, man.
Okay, so what's this A-tan 2 business? Probably most of us, I'm sure, have had contact with it at some point or another, but the brief answer is that if you've got a full circle, and let's say you're in this kind of situation right here, and you're trying to find this angle phi, you would do, let's say tangent of phi is x over z. So therefore phi is the arctangent of x over z. But what happens if this actually is completely opposite? So it's in the opposite quadrant. That would be arctangent of negative x over negative z. So they cancel. And so things at opposite coordinates will give you the same value from the regular arctangent function. That's the first sort of issue with it. So if we want to recover an angle from the entire circle, there's this special version called A-tan 2. I think it was from the 60s, according to Wikipedia, which I just find funny that they made a sequel to a math function. They didn't bother naming it anything else like A-tan 2. Yeah, even better. So instead of it's a two-argument function, and it actually looks at the negative and positive signs of the input that you give it, and it assigns the correct quadrant based on it. That's the first thing it does. And the second thing is there's no division by zero problems. Because plenty of times the denominator will be zero. Like if we're in this case here, if we're steering straight to the right or straight to the left, we'd have zero in the denominator. And A-tan 2 will just tell you, oh, we're straight down this way, so it'll be like, 90, -90. If we're straight on the right, if the numerator was positive, and if the numerator was negative and the denominator was zero, we're 90 degrees positive. So that's A-tan 2.
Thank you. That's a really helpful explanation. That is really weird. That like doesn't seem like a math function. That definitely seems more like
It came
just
up
like
in floppy.
piece of code.
Well, maybe I didn't
Like-
mention it, but it came up in floppy.
Oh yeah.
Yeah, because I think initially I implemented like flops for A-tan, and then I realized we're using A-tan 2. So there's slightly, so A-tan 2 is quote unquote superior in a way that the output is from minus pi to pi. So minus 180 to 180, it covers a full circle, while for A-tan, just a normal A-tan, it's like minus 90 to 90. So if you just do A-tan of a point that's 1, 1, that's 45 degrees from the x-axis, right? Counterclockwise. But if you do an A-tan of -1, -1, which is in quadrant 3, like you just mentioned, that's also still 45, even though it's technically like 215, right? Like if you go -1, -1 in the xy coordinate system, so it fixes that. Like with a so with the A-tan, because it takes a ratio of the two, 1/1 is the same as -1 over -1.
Right.
But
Yeah.
not an A-tan 2.
But yeah, it's just weird. It seems like a lot of like if statements rather than like a smooth continuous mapping between two number spaces. I don't know. Yeah,
Yeah.
it's weird.
Yeah.
I have a-
But the practical tip is probably use A-tan 2.
Yeah,
That's probably the right thing to do.
if you only ever care about magnitudes, then fine. Go ahead and use ATAN. But if you're on a plane, like a full plane, a full circle, you want ATAN too.
Yeah.
The sequel, bigger and better, more complete. All right, so I have these that are ready to get pushed into Monty because I just figure these are the ones we should use. This is the exact form we should use always, unless there's some weird case. If there's some weird case, then you're responsible for it. But otherwise, if you need to do mappings between Cartesian and spherical coordinates within Monty, within our conventions, these are the forms. So those will go up into, I think, transform utils is where I was going to put that. All right, so then mapping back from spherical to Cartesian, that does also happen, and
Yeah, and just to make it a bit concrete, so in Monty, where do we use those transformations? Is that when we want to go from like where we are in space to translate it to a movement vector of the camera, like turning it up and down and left and right, or is that draw pitch?
so the spherical coordinate would tell you basically how much yaw or pitch there is relative to your 3D reference frame, your Cartesian reference frame. So yeah, if you're
Yeah.
trying to figure out, there's a point over there, I'm facing like this or whatever, like
Yeah.
like that. There's a point over there. Then this
Yeah.
formula will give
So for
you.
example, you're using this for the saccade work, like you have a salient point over here in your field of view, and now you want to look at it. And so you have the salient point in spherical coordinates. Wait, in Cartesian coordinates, and you want to convert it to spherical so you know how to move the camera?
Yeah,
Okay, cool.
exactly. So I think I put it down here. Euler angles are mostly necessary when we're dealing with camera data because there's projective geometry involved, but also the motor system because we speak to the motor system in terms of angles. We can't just tell it, here's my point in space. We actually have to be explicit about how to get there with an actuator.
Yeah.
So the points in the code where we do have to do this, there's the saccading to targets. There is get good view, which is basically the same deal. And then sort of one of the other main areas, I'm just going to point this out as sort of a counterexample, is I was looking at I think it's in the voting math where there's two rotations and we need to figure out sort of orientation between them. It's close, but in that world, you don't have to deal with Euler angles at all. You can just compute the rotation that takes you from one system to the other. You can just generate a matrix. And you don't have to deal with the headache of Euler angles at all because Euler angles are a bit of a headache. When you get them, the first thing you should ask yourself is, what order do I apply these in?
Yeah.
Do I
Oh,
first rotate around the x-axis and then the y-axis and then the z-axis? And the second question is, if I first rotate around, let's say the x-axis, so I pitch up a bit, and then I'm going to rotate around the y-axis, do I rotate around the new y-axis? Because that's changed now. Or do I rotate around the sort of external y-axis, which is, I can demonstrate this in a bit later, but this is the difference between extrinsic and intrinsic. If it's intrinsic, it's like you always rotate around the new axis. So I apply the x rotation, and then I apply rotation around the new y-axis, and so on. So when, for example, we're doing scipy dot rotation from Euler, x, y, z, and then some coordinates, if they're lowercase x, y, z, if I'm not mistaken, that's intrinsic. And we applied them in the order x, y, z. So this is something I didn't get to in this presentation, but in any sort of action-related space that we have in Monty right now, you want to be applying y and then x. So, but when it comes to trying to figure out, hey, what was the object's orientation that habitat was doing? You want to be doing it in order X, Y, Z, and then and intrinsically. So that's another just a trial and error thing. But yeah, so if you see Euler angles, just I hope bells go off for you. What order do I apply these in? And is it intrinsic or is it extrinsic? Um, that's
Question.
the
Yeah, I think SciPy forces you to specify it. Because
Yeah,
Yeah.
and
remember the
whenever I
first
have to
time I
specify, I'm like, I
wrote the
don't know,
function.
but I'm gonna put X, Y, Z.
Yeah. The first time I
That's always
wrote it,
what
I was
happens.
like, oh, I don't know what this even means. I just want you to rotate it. And then I
Yeah,
went like, oh, okay, yeah, it does matter. Thanks for
yeah.
asking me about this.
They always
Uh,
say, the order matters and things like that, but it's hard without like good visualization tools to internalize what that means. But I'm gonna pull up Blender later, and I can show you guys how to use something like that as a visualization tool for this kind of thing, and kind of make it a bit more obvious. I wish there was some kind of just online thing you could go to that I just plug in, just play with rotations. That'd be kind of the cool thing, but I couldn't find one.
And
oh,
does that still matter if it's done extrinsically?
The order of application?
yes,
Yeah, I'm guessing it probably still does.
Yeah.
yes, yes.
Or does it
Yeah, okay.
does it depend on like essentially the affordances of your effectors, right? It's like
Yeah,
if you pitch up and your effector can only go intrinsically, versus if you're on a platform and you pitch up and your effector can go like this
exactly.
would be
Yeah,
extrinsic, but this would be intrinsic, right?
that's
Yeah.
correct.
So it was so confusing for me because I'm so used to thinking about as if you're like an airplane. Like the idea of why a gimbal lock would be a problem ever took me a while to understand because I'm just not used to thinking about one actuator that can do one thing mounted to a thing that an actuator that can do another thing. I'm used to thinking about just these free floating, spaceships basically. They can always yaw around their own axis and so on. I was like, so you point up. What's the big deal? It's like, but no, you lose the orthogonality of these, um,
Uh,
uh,
yeah. Can we, is it possible to like talk to the motor system in not angles, but just, I know you can say like, oh, you can't just say, go like look at XYZ and it will just do that for you. We have to like give it some kind of angle, like, okay, like rotate, yaw, pitch, whatever in 45 degrees so that you can actually look at this. But like because Euler angles are so like my wish I guess is like I think I expressed this to you is like Euler angles only for defining the cube and rotation faces like the 0, 0, 0, 0, 90, 0 and like the final like human readable output like oh here's the predicted orientation of the object at the end, but everything inside is just we just use rotation matrix and we don't need to worry about intrinsic or extrinsic because we just need to multiply by rotation matrix.
so I'm going to make the case for the opposite, actually.
Oh no, okay.
Yeah.
To use Euler angles everywhere,
So
or
the case that I'm going to make, unfortunately, I didn't have time to put any materials together on this, but um, in a simulator, say like or robotics, uh, let's say you have a joint you can rotate around. You define that joint is defined by an axis of rotation and the amount,
mhm,
and that's it.
mhm. Okay, so there's okay, so we do need to communicate to the motor system that way. Like,
Yeah,
yeah,
and
Well,
like even internally, so Majoko, for example,
yeah,
when you issue a change,
yeah,
all it does is make new joint coordinates. It just, if you say I want to rotate 10 degrees around, uh, I want this joint to rotate 10 degrees, it just adds 10 degrees to that coordinate.
yeah,
These are your generalized coordinates. It doesn't
yeah.
give you a 3D reference frame for each point along that um,
Got it,
chain.
got it.
You compute it yourself, given the axis of rotation at that joint and how much. So this
Yeah,
sort of forward pass, you can kind of recover the full Cartesian reference frame for each node. But
yeah,
internally, it's all represented through just amount. And actually, I
yeah,
think the reason I'm making the case for thinking about it more seriously this way is because I think if we're trying to issue commands, if we're trying to
Yeah.
actually learn commands,
Yeah. Yeah.
we want to be able to just like
Give it
learn a
a command.
parameter. Like this is how
Yeah.
much you need to spin.
Yeah.
Well,
Yeah.
but I think I want to talk more about this because there's a future Monty and there's today's Monty, and I don't think today's Monty should be using Euler angles inside of it except for as an output of the motor system. And the reason for that is like our current learning modules don't have an embodied model at all. And so they just care about a point in space. And for that, we can use matrices or quaternions. And that can be part of the goal state to the motor system. Motor system will then, it's motor system's responsibility to then take that space and figuring out how do I actually act on it. And that's where the conversion can happen, I think.
Yeah.
In the future, Monty, and because motor system right now, we're essentially going to hand it an embodiment, what I call embodiment oracle. It's like you magically know how your body's put together and how to translate out in space into using this embodied oracle that we just told you this is what you are, how you are put together and where you are. In the future, Monty, when that embodiment oracle becomes learned inside learning modules, that's when maybe we might want to drift away and start doing what you're saying. But I think it would just become too complicated now. Like none of the learning modules today have any business learning how to move. Until
I'm in
we
agreement.
actually
I'm
go
in 100%
after.
agreement.
Say again? Okay.
Well,
I'm in 100% agreement on that. I just you know, I'm just
Yeah.
sort of dreaming forward, X
Right.
number of
Yeah.
months or years to when we are learning to control a motor system. I'm thinking, well, we have to do it in the coordinates of the actuators. And the coordinates of the actuators are angles, like amounts, basically, if it's a rotating
So
cuff. So yes, in the time for the time being, like until we have a learning components that learn how to do motor commands, there's no reason to do anything in Euler angles or anything like that. But
and I'm in your agreement with the future.
yeah,
but
okay.
yeah, I mean,
And
that's
I'm
kind of
convinced.
how it is right now, right? Like goal state generators emit locations, like they don't emit Euler angles as far as I remember. And learning
Yeah.
modules like hypotheses and all that are all rotation matrices.
Yeah.
So I don't think we
Yeah.
are using Euler angles inside Monty right now, except for the human readable output, like the logging.
Yeah.
Yeah.
Yep.
Yeah.
Yeah,
So I
and then in
think
terms of
Yeah.
the motor outputs, I mean, just to clarify, because you're saying two Euler angles, but are the spherical angles Euler angles or
yes.
okay. But
Euler angles are an amount
yeah,
of
just when you
rotation about a
specify the
certain axis.
degrees.
Yeah.
Yeah, and then here you just have two
Yeah.
rather than three. Okay.
Right. And we never use radius, or we haven't thus far. We're not doing full conversions, but we just use these two when we do, like say do actions. But um, yeah, I think there's some literature out there about vector cells and things like that. There's stuff going on in the brain that is up sort of in this space, in this type of representation. And I'm not an expert on that area. I read a little bit about it maybe a year ago because I thought, oh, that's interesting. But yeah, so it's kind of like these things are in the brain, and you can kind of imagine why. If I hear a bang over in this direction or anything like that, I only really need to know the I don't need to know where that is in 3D coordinates, full 3D coordinates. I just need to know how much to move to get there. Though you could
Yeah,
use like
especially for like the model free kind of stuff.
yeah,
But
exactly.
it's interesting because actually with the insect path integration talk I saw, they were trying to figure out whether ants, for example, use more like polar versus Cartesian coordinates. and they basically initially they were like, oh, it's probably going to be polar because it's kind of simpler and stuff.
Right.
But actually, they realized it's probably Cartesian for various reasons. But I think that fits with kind of learning modules still being more kind of Cartesian. And I think this
Yeah.
also fits with what you were saying, Tristan, that like within the learning modules, they just care about points in space. And then, yeah, it's more like motor system where it's like, okay, now I need to move this by a certain amount.
I do have a
Yeah.
question.
Yeah. Sorry. Go ahead.
I do have a question about because you said a specific phrase. I just need to know how far to move at this angle or whatnot. Are you sure it's how far to move and it's not how much force to apply over how much time?
Yes. No, I'm not sure of anything.
Okay,
You know,
I
I
just
don't really know.
but I just want to throw that in, right? That like
Yeah.
it might not be communicated in move this many angles. It might be communicated as flex this muscle this fast and
Yeah,
relax the other
it could be
muscles.
anywhere along that. Like I think ultimately it's going to be
Yeah,
uh
that's probably like the final step in it. And that's probably why, like, if you think something's heavy and you go to pick it up, then it's like, oh, your arm flies up because you apply like a large force or whatever. But I guess what
Yeah.
was informing that muscle contraction is probably something like, oh, I want to move my arm by this amount.
yeah. I think we've kind of danced around this argument a little bit. Like I'm always willing to entertain the idea that there's more polar happening than there than than we might expect, but I'm open to it. You know, I don't really know. Like because when I think about situations where the depth is ambiguous or unknown, or even just on a flat plane, like I'm watching TV or something, I don't have a sense of what the depth is. I'm not computing, you know, or it's like something that's hundreds of meters away. It's like I'm really just kind of saccading between 2 points. They might as well be of infinite distance, or you know, or they could be close, but I can still saccade to them because all I need to know is sort of the angular distension between them. So I think there are cases where this seems like there's kind of strong cases sometimes for more polar representation when it comes to cases like that, but you know, it's debatable. Yeah. Anyway, um, we also did. I brought this up at the focus week, and he said, yeah, you could actually just sort of adjust your saccade amounts based on sort of an expect like the distance from you to that billboard, but it feels like you're asking a lot of your depth, like your ability to compute depth, especially on the fly. If you're trying to do all of your eye motions um, uh, in Cartesian coordinates, especially when like V1 and the collicular surface is basically sitting there in angular coordinate, you know, spherical coordinates, more or less. So it feels like very easy to extract. If you need to do a real quick motor command from here to here, it's kind of already in that. It's already in those coordinates, basically.
Yeah, it seems like maybe the kind of more subcortical parts like the sensor module and the motor system can do spherical coordinates. Like when you're doing saccading to something salient over here, I agree with you. Like you probably don't have a very accurate depth estimate of that, and you probably don't need that to calculate how to move there. Like you don't need to go through Cartesian space. But that's more like a model-free movement that would be based only on sensor module information.
Yeah.
But then once you go to model-based movements based on like actual structured models you learned, as in the learning modules, I would say it's probably going to be Cartesian based.
Yeah.
Yeah. Or I guess this might be a case where even if it like turns out some biologists found out that it's spherical, like we might still stick to like matrices based rotation in the learning module just so for computational benefits, possibly.
Yeah.
Yeah, but yeah, okay, yeah. I think I'm convinced, but yeah, and I think I didn't come to this kind of same conclusion because I didn't work with the motor system yet. I think I'm the
Mhm.
last one, maybe, I don't know. I remember when you started this Coordinates, I got to know anything about the motor system, and now you're an expert, and I'm still like I still don't know about that motor system. So maybe
Well,
after my 2D sensor module,
yeah,
like
I'm
I don't
hopefully,
know.
just submitting these transforms to Monty will make the process,
Yeah,
so you don't have to think this through every time.
yeah. I, I guess my ideal world is that there's no body and our agent is just an infinitely small point, and you can tell it to look at any XYZ and it'll just do it.
Yeah,
But then it's like that's very non-real world.
yeah.
Yeah, anyways,
Oh, before I forget,
yeah.
I did want to say that the azimuthal angle is defined between, Jose mentioned this before, between like negative 180 and positive
180.
180. So you get the full circle, but the polar coordinate, that's just straight down to straight up. So you've got 90 degrees there. If you
Oh
tip
yeah,
past,
oh yeah.
that's actually
Jesus.
equivalent to as if you had done a 180 in yaw plus like a little bit in the opposite direction of polar. So just something to
Yeah.
keep in mind.
I think you just triggered like a calculus memory from high school. I just got a flashback.
You're welcome.
Yeah, thank you.
Okay, so here's something that was, let me see if I have time for it. So this puzzled me. If you compute phi here, this azimuthal coordinate, you only need x and z. You can just look straight down from the plane. But when you want to compute the polar angle, or I said I wasn't going to say polar, but elevation, you need to get x and z involved. You need to get all three involved. So I think, okay, so my first mistake was just thinking you could do the same projection for the polar angle. I mean, why not? Just project this. I mean, what's special about pitch? We live in a world where, no one direction is privileged over any other. So what's special about uh about this? And so this was a bit of a mystery for me, but hopefully I can clarify. Maybe it's completely intuitive for you, but for me it was like it
I mean, yeah, is it not just like the reason you were just describing that there's kind of the way the coordinate system is defined is kind of privileged for one of the, as in like if you tip backwards, then you're going to start reverting to another. Is it, or is it like related to that?
yeah, I hadn't thought about that. But yeah, it is basically like,
So kind of
so
one of them
okay, so
has
here's
to.
here's how I'm thinking of it. This extraction maintains like orthogonality in a sense. Otherwise, these two things can be sort of non-independent. So when you perform an action, so again, this kind of comes back to we're in a situation where we have to decide in advance we're going to be performing a motion in sort of a sequence. These are Euler angles. We have to think about the order in which we do things. So when you do a command, we're actually rotating our um, polar plane. We're trying to get that dot onto this sort of meridian, right?
Sorry, just to clarify, what is what? So the dot is
So the dot is a target we want to look at, for example. All right.
okay, and the
So
direction we're pointing in is the dash line.
yes. So we need to, when we yaw, we're rotating that whole this vertical plane here. That's our plane that we're going to be moving our up-down guy in, our sensor module or whatever. So if you just sort of project onto the y x plane to try to get that pitch amount, you're not taking into account the fact that yawing is going to change what that axis is. This version of the elevation coordinate is independent of yaw.
Yeah, I
As
think it
in,
makes for me.
if you perform a yaw and then do this one,
You're
it
good.
kind of you're good. Yeah.
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 Otherwise, what you have to do is do this first yaw motion, stop, take another measurement. Now compute the polar angle in the really simple way, which you just project it onto the y-x plane and do the motion. That's what would
I guess that makes
correspond to.
sense. Yeah.
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 Okay. Let's play that out again, I can't have wasted having learned how to do that in Blender. Okay.
Yeah, that's a cool animation.
Yeah. Really
And
nice.
so do you always yaw first and then pitch?
Yes.
Okay, and if you did it in a reverse order, you'd get a different result, I guess.
Like if you did it in reverse order, you'd have to uh compute those angles differently. You'd have
Oh,
to
okay.
basically
Yeah.
flip the way that you do that, you know?
Yeah. Okay.
Yeah. So
Life would be terrible if we had to always like move like this.
yeah, I mean, it's so much easier in a way to so here's a fun fact about rotations is that any rotation like this, any Euler, series of Euler angles, you can do that whole series of rotations. Like there is an axis in space somewhere, a single axis, and a rotation amount that will get your reference frame from the original one to this one. So if we just magically had an actuator that happened to have that axis moving along that direction, then it would be easy. We would just say, okay, spin by that much. But we don't have actuators in every axis, in every direction. So we do have to, um, work within the confines that we have for the rotational axis that we do have. But that is a cool fact about rotations. Um, I'll leave the exercise to the reader, I guess, to work out exactly how that works. Okay, so I figured we could give this a shot, and I'm going to pull up Blender, and let's try this.
Which coordinate convention does Blender use, by the way?
Coordinate convention is Z up, X to the right. Actually, can you tell me how small all this stuff is? Like, can you see this little widget up the top?
Yeah.
Yeah.
Okay. If it's helpful, I can turn on like axes to try to
Oh,
remember
yeah, nice.
where we are. But for the time being, I want to try to forget about that just for the purposes of this little demonstration here. So here's my little uh, two degree of freedom gimbal, which is what the system is called, where you've got a rotating thing, like a yawing thing, and then mounted on top of that, you've got an actuator that moves in another direction. It's called, 2 degree of freedom gimbal or free gimbal sometimes. So you can't really tell right now because these things are right on top of each other and they're co-aligned. But if I grab this sensor real quick and pitch it like that, you can see that these are starting to come apart. So I've encoded sensor stuff in red and including this ray here that's pointing out. It's a sort of targeting ray that's in red. for the sensor. And in black here is the agent. So this is the agent's reference frame, and this is what he's pointing towards exactly. And this sideways one, that's our x-axis. They're always co-aligned. So it looks black, but that's just because alpha blending is like, the reason it looks grainy is because of alpha blending. It just like looks a little bit funny when you're trying to render it live like this. All right, so I'm going to reset. All right, so our first goal, and this box here, I'm going to get rid of it in a second, but that is our camera. I've mounted a camera onto the sensor so we can actually go ahead and see what the sensor is seeing. All right, so let's go ahead and sort of simulate having to do this process. So I'm going to go sort of determine what our yaw angle ought to be to get to that guy first, and then we're going to try to get to that guy. But first, I'm going to go into this top-down view here, and I'm going to, in lieu of doing trigonometry, I'm just going to grab my sensor here and say, how much would my sensor have to yaw in order to get to that? Okay, seems like about 30 degrees. All right, great. Now, what if I were, sorry, what if I were over here? So I can kind of just do this and try to figure out how much we'd have to pitch the sensor. Oop. Okay, looks like
Yeah, that's the
Wait, was
wrong
that the right
sphere.
one?
oh, sorry, yeah,
I thought
sorry,
it was
you're
the
right.
stripy
Yeah,
one.
it's wrong. I was like, shoot, did my demo change? Okay, it's supposed to be about 40, 45 degrees, something like that. Yeah, shoot, it was supposed to be 45. All right, but this demo will work anyway. It's okay. All right, so let's go ahead and execute that now that we've computed it. So I'm gonna go ahead and yaw this thing. I'm gonna yaw the agent because the agent yaws. I am the agent who yaws. I'm the agent who yaws.
I got it.
So we're gonna go 30 degrees in this direction, and then we're gonna go ahead and pitch up the sensor. I'm gonna grab my sensor and pitch it up by, all right, let me just go into camera view here, see how we're doing. Pretty good, 45 degrees. All right, we're right in the center there. There's a little red dot from my targeter, but it's, it's dead on in the center. All right, so all good, right? I guess maybe the quickest thing to demo here would be actually just to show that if I do this in reverse order, just gonna go ahead, reset everything. So now I'm going to pitch the agent first by 45 degrees. And then I'm going to swivel the agent by, wrong direction, 30. And if I look at the sensor, it should be slightly different. Oh, no, it's not. Okay. Oh, okay, forget it. Oh, because they were co-aligned to begin with. Never mind. That matters more for the second pass. But anyway, all right. So now imagine we need
the yaw was extrinsic, right? Agent never pitched with the pitch. That's why.
yeah.
So
okay,
but
but
an extrinsic should work.
right. So now we're no longer aligned. So if I try to do, I've got my sensor and I've got its camera data, and I'm going to try to figure out how much I need to pitch and yaw to get over to the second target. So I'm going to try to simulate what we just did there. I'm going to try to get a good exact sort of orthogonal projection of what the sensor is seeing. A bit tricky, but I'm trying to get that z-axis straight on. Say, how much would my sensor have to yaw? I'm doing this the wrong way, by the way, on purpose. how much would my sensor have to yaw in order to get over to that point to hit that thing? It's like 90 degrees. That's how much my sensor would have to yaw.
When you
Okay?
said you're doing it wrong, are you saying you're yawing the sensor instead of the agent purpose?
Yes.
Okay, got it.
I'm
Thank
trying
you.
to show what a mistake that could be made here. All right, so okay, I go, okay, great. 90 degrees would get me there. I'm gonna reset that. How much would my sensor have to pitch? I'm gonna try to get exactly, dead on like that. Oh, it looks like I don't have to pitch at all. I'm already like right on target. Great. So if I just tell my agent to yaw 90 degrees and I don't pitch at all, well, let's just go ahead and see what happens. Tell my agent, go, what did I say, 90 degrees? So we got to go up to positive 60. Who's about here? We're way off. Okay. So this is why it's important that when you're computing the yaw amounts and pitch amounts, but yaw amounts and stuff, you have to do it in the agent's reference frame. But then, and say, how much would the agent pitch to get to this? And then subtract the amount that I'm currently pitched at, which is one of the reasons why it would actually be nice to have an internal memory of what the current joint angle is. Instead of having to recompute what the current agent pitch is or sensor pitch, you just already have access to it. But that's kind of another story.
And I guess is part of this inherent to the 2 degrees of freedom gimbal? Because I guess if
Yes.
you had a sensor
Yeah.
that could yaw, then you could just do that.
Yeah. So
Yeah, I was gonna ask, like, is it habitat where our sensor is attached to our agent in this 2DOF way, or can we make it like a ball and socket joint?
I don't think there's anything preventing us from doing that, but all the
Okay.
commands that are being issued for all this stuff within the code base are all turn left, which is an agent yaw, turn left, turn right, and look up, look down. And those are
Okay.
sensor commands.
Okay.
To my knowledge, I mean, maybe it is. I'm not familiar with the way Habitat simulator is like configured, so
Yeah,
maybe
I'm
the
sure there's-
sensors can actually yaw independently on their own. But this is when I realized something was wrong with my understanding of Monty and probably, geometry. So I was like, what is going on here? But I could not shake the idea that an agent ought to be able to yaw along its own axes like this. That it
Yeah.
actually that a sensor would be able to continue sort of using its own rotational, So when I was trying to compute coordinates, they're usually not this extreme, but the targeting would be off by a
Yeah.
little bit. And it was because of this issue of trying to compute the amount of yaw. It's natural because the data you get comes from the sensor. It's in the sensor's reference frame. I mean, it ends up being in the world reference frame, but then you have to, forward map it into the sensor's reference frame to figure out how
Yeah.
much to yaw. And then,
Yeah.
so you go, oh crap, there's this mismatch. What exactly is going on here? And the issue is, you need to be thinking about how much to yaw in the agent's reference frame.
Yeah.
And in terms of pitching, you could do that in the agent's reference frame, but you need to, obviously account for what the pitch currently is for the sensor. I mean, you ought to be able to do it just from the sensor's reference frame, and I do it in here just fine. I could do
Yeah.
it in do agent yaw in the agent's reference frame, and do sensor pitch in the sensor's reference frame. I tried it and it was fine. But when I did it in Habitat or in Monty, there's like slight differences. I'm like, I'm
Yeah.
still not really sure what's going on there, or if I made a mistake because it's so easy to make little mistakes. You miss a
Yeah.
sign or whatever. But
But
Yeah, it's
theoretically,
really
if
nice
we
with this
make it-
visualization and intuitive, but I can totally see how this would be pain to debug if yeah.
Yeah. So theoretically, if the joint type is not 2 degrees of freedom, but 3 degrees of freedom, like we would worry less about this, right? I guess it
Yeah.
depends on kind of the robot that we get, but I think a lot of our joints are 3D. I'm just like trying to do weird joint things now.
I mean,
Just like,
certainly
what are 3
eyeballs
degrees of freedom?
are more of a ball and socket than a Yeah.
So
I'm
Yeah.
assuming, I don't know if there's some weird, just some historical thing of when Habitat was implemented, because or like the interface, because I'm sure we can do look left and look right rather than turn left and turn right, i.e. sensor, if we wanted to.
So,
Yeah.
here's another thing I want to kind of pitch around this, right? Because this is just a historical path that got us here. But when I was thinking about like how would I do this from scratch or whatever, there would be just a single position action, and it just sets the entire pose in space, and that's it. And my question is, we just said like this is all very valuable for embodied motor system. Kind of to Jose point, we are in a simulator. Everything, all our experiments, like what are we trying to do today with Monty, right? Are we trying to control a body, or are we still trying to figure out how learning modules ought to work? And the reason I'm posing that is because we can probably substitute everything to be a single action, which is position 3D, and we give it where it needs to be and what pose it's in, and it just goes there. We don't need to do yaw, turn left, turn right, turn everything else. We can just say, just appear in this position. In a simulated environment, like that might be enough for all the near-term experiments we want to do. And then we can tackle this when we want to work with embodied things.
So I want to make 3 points really quickly. First is we did a robotics hackathon. We are attempting to occasionally, do stuff in the real world. So, I don't know, maybe it makes sense to to I'm not pushing back. This is just, a sort of counter argument of, while we're trying to learn as much as we can and develop as much as we can in sort of fundamental research area, if we are going to try to validate or, get engagement in the robotics world somewhat, then maybe it's worth keeping in the back of the mind and not, but in support of your point, the surface agent doesn't care about any of this stuff. It does set agent pose. It just does warp. It warps to where it needs to be. And it's certainly,
The goal state does that, the jump to goal state.
yeah.
But the surface agent doesn't warp. It does like a complex 4-step trig based thing.
Oh, it does.
Yeah,
Well, it sets
that's
agent
at least my
pose.
understanding. It basically does this thing where it kind of looks at the next surface normal, calculates what rotation it needs to do to
Yeah.
face that, and then shifts along a tangent and all this kind of stuff.
Sorry, yeah, I should have clarified. It was when it's trying to execute a goal state. That's when the surface agent
Yeah, the
sets
jump to
set
goal
agent
state is
pose.
exactly what you're describing, Tristan. Like we were just like, we want to see what effect this has on learning modules. We don't care how it's achieving that. So
Yeah.
we're just going to set the pose.
And I think if we had to work out all the kinematics of getting the finger to that point, that wouldn't have been a productive use of time, for trying to figure out, so I'm in agreement on that side. But I would just say, having to think about this, I think ultimately was a good thing for me personally. Uh,
Yeah.
This
very
is
much,
how
yeah,
hazing starts,
so-
Scott. You're like,
I know,
I
right?
had to go
Yeah.
through this, so everyone
Yeah.
else should have to go through this.
I think it did help me
No,
think, like, have a longer term view of what I think a motor system might look like that can learn. So, it's, so I think people ought to be able to do anything they want within Monty with just warping, setting the agent pose, sensor pose, yeah, as a totally almost like a disembodied thing, like a point, like a being of pure light that can just, uh, but at the same time, maybe there's some value to occasionally having to think about what contact with physical mechanisms is like. But that's more of like a personal matter than,
I
an
think a
argument
middle
about.
ground, like with the whole like, oh, like I've been thinking of, like I didn't give any credit to embody, and I just think of Monty as this 1 point thing that's, that you can give a position XYZ to, and like that's the ideal. But technically, I guess if we think about like 2 sensor modules or, like more, then I don't want them to be like 2 separate things that just they're together. They must be connected to like an agent or a couple agents, and there must be some relationship between, let's say, one agent and we have two sensors. I guess the easiest would be if, again, the joint is a ball and socket, 3 degrees of freedom, so that things can be independent. But
Mhm.
in that sense, like there is some sense of bodiness when we, like, when I think about more than one sensor module. At least I'm thinking about like how they are kind of related to each other in some sense. And
Yeah.
probably like in real life, we probably don't want like things to be crashing. But I mean, I'm not gonna worry about that now.
Yeah, and for what it's
Um,
worth, I mean, we do already, even with our beam of light, have kind of issues with the jump to goal state where it can appear inside of objects and stuff like that. And so there's kind of some very
right.
crude code to try and deal with that situation. But like, I guess the advantage of not just setting a pose is that you tend to do it as more incrementally. And so I think it does force us to think a little bit more about policies. But yeah, I don't know. I think it's a balance, and I think we've been treading a reasonable balance so far. Because I think you're right, Scott. There are advantages to thinking through these things, and it makes it easier if we actually want to do things like robotics and stuff like that. That it's not like the first time we've ever kind of
Yeah.
had to do small continuous movements. But yeah, we had the exact thought when we wanted to add the goal state thing that it's like we don't want to try and figure out how to get a surface agent to like move across the surface. Like that's going to be super complex. Um,
Is that what I'm supposed to be doing for 2D sensor modules?
yeah. Well,
It's gonna be super complex.
it's
So let's
related
make
in a local
I'm just
neighborhood,
kidding.
but at
Yes, I
least you don't
know.
have to like move to the other side of a 3D
Right, right.
object.
And I mean, another argument for it is also like for doing the teleport in a simulator until we actually focus on robotics is that robotics, it's not gonna, I mean, disregard. I don't have a clear thought yet.
I mean, I don't
Yeah,
know
I
if
mean,
this
I
is
think
what you were
it's
kind of thinking, but like, I think there are a lot of these things that we wouldn't necessarily want to compute or even implement ourselves. Like inverse kinematics is like a huge field. There's also like, reinforcement learning, neural network based methods to kind of move systems based on, so we could imagine Monty as again the cortex, and then all these other systems, whether it's evolution or Boston Dynamics or someone else that's implemented it. We just kind of leverage that, and then it figures out how to actually move.
Yeah.
Yeah, maybe 2 years later, once we figure out the cortex, we'll just hire a roboticist and he or she can help.
But I guess I'm just discounting the research effort on non-learning module learned embodiments, right? Like this will all like I think all this is extremely relevant when we commit to learning modules now figure out how to model the body. But before that, it just seems just dipping the toes in, but it just feels like a friction at any step before that. With the idea that when learning modules just say you need to appear here, any code between that makes that happen is just an expense that will need to, one, go away when learning modules learn the body, and two, like if we're in a simulator, who cares?
Here's another pitch, another angle, I guess, to think about is warping pretends like time isn't continuous. And we would eventually like Monty to figure out how to live in a continuous time world. And that involves a lot of sensory input on the way towards accomplishing that goal state. Sensory input, which we may want to sort of, I don't know, maybe we want to cut down on what happens in the learning module. Maybe not, there's going to be a lot of issues in terms of how learning modules function during the execution of motion and things like that in a continuous time world, where I think that's, and, involves time I think these things are fundamental to the brain. And even though the kinematic control maybe is something we can put off, the actual mechanisms that we use to position joints and things like that, figuring out how to have Monty behave in a continuous streaming sort of world where we don't warp. I think that actually is kind of a non-artificial and actually kind of a fundamental uh,
Yeah, but I think my challenge to that is I think you're imagining warping as somehow just going huge distances for no reason. All I'm saying is you can trace a path just by setting set pose, set pose, set pose, set pose, set pose, and you can get everything you just said just without worrying about how move right, tangent, you're
true.
up and whatever. I just be like here, 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 here. So we can. So I'm not advocating for ignore continuous motion. What I'm advocating for, if you're gonna do continuous motion, just say I'm on this path that I magically calculated because I can.
Yeah, I'm good with that. I think that's a great sort of middle ground where we could experiment with trying to figure out how to deal with continuous streams of information without having to fuss with actuators and things like that.
Yeah, and Monty we have already, or for Habitat we already have the actions for set pose and set pitch for
Right.
the agent. So it's easy to just use those actions wherever it's easier than using relative actions. But yeah, I do think it's still useful to understand these concepts and understand everything you just presented, Scott, because I feel like everyone has come in touch with these things before, not necessarily in terms of action policies, but also for visualizing things, for loading models into Habitat, showing objects at the right location relative to the agent, stuff like that. So it's, yeah, like I think the general topic of understanding all this is still useful in a lot of ways.
Yeah, and I'm not sure there's any reason we would want to go in and change the existing ones, but I think it's a fair point that if we want to add more action spaces, then yeah, like you're suggesting, Tristan, yeah, just remember that we have ways to just set these things. Um, but
Yeah, I think
yeah,
from my perspective on sort of the daily work is my um, goal for myself is just to, if there are these policies, like look at policy that makes assumptions about the kinematic chain, then just be clear about them. So, so a future me doesn't try to just plug in, look at, thinking that it's going to act in a different way, or it's going to pitch and then yaw or something like that. So it's just as just a matter of practical practicality, trying to be as explicit as possible about the constructs that are assumed and actually required for different components, really just policies and parts of the motor system. And so that's my plea, I guess, is that any bit of motor code just says what the assumed kinematic chain is in the top level doc string, basically.
that seems fair.
Yeah. I don't think I have anything else. So.
That's real nice. Yeah.
Yeah, really awesome.